Time, for most of us, is a constant, unwavering rhythm. It dictates our schedules, marks our memories, and guides us from one moment to the next. We perceive time as linear, always moving forward, never stopping or reversing. This intuitive understanding is deeply ingrained in our daily lives. We rely on clocks to measure its passage, calendars to track its progress, and the steady beat of our hearts to remind us of its relentless march. However, this seemingly simple concept of time takes on a whole new dimension when we delve into the realm of physics, particularly Einstein's groundbreaking theories of relativity. These theories challenge our fundamental understanding of time and reveal its intricate connection to space, forming a unified fabric known as spacetime. This cosmic tapestry of spacetime is not a static backdrop but a dynamic entity, capable of stretching, warping, and even stopping under certain extraordinary circumstances. This essay will explore these mind-bending concepts, unraveling the mysteries of time dilation and the possibility of time coming to a standstill in the vast expanse of our universe. Imagine a trampoline. If you place a bowling ball in the center, it creates a dip, a curvature in the trampoline surface. Now, if you roll a marble across the trampoline, its path will curve as it approaches the bowling ball, drawn towards the dip. This is a simple analogy for how gravity works in Einstein's theory of general relativity. Instead of a trampoline, imagine the fabric of spacetime, a four-dimensional continuum where space and time are interwoven. Massive objects like stars and planets create warps in this fabric, much like the bowling ball on the trampoline. These warps are what we experience as gravity. This revolutionary idea, proposed by Einstein in the early 20th century, shattered the Newtonian view of gravity as a force acting at a distance. Instead, Einstein showed that gravity is a consequence of the curvature of spacetime caused by mass and energy. This curvature affects not only the paths of objects but also the flow of time itself. Einstein's theory of special relativity, published in 1905, further revolutionized our understanding of time. This theory is based on two fundamental postulates. First, the laws of physics are the same for all observers in uniform motion. This means that whether you're standing still or moving at a constant speed in a straight line, the laws of physics will apply to you in the same way. Second, the speed of light in a vacuum is constant for all observers, regardless of their motion relative to the source of light. This seemingly simple statement has profound implications for our understanding of time. One of the most startling consequences of special relativity is time dilation. This phenomenon predicts that time passes slower for objects in motion relative to stationary observers. The faster an object moves, the slower time passes for it. This effect becomes more pronounced as an object approaches the speed of light. Time dilation, a direct consequence of Einstein's theories of relativity, challenges our intuitive notion of time as a universal constant. It states that time is not absolute but rather relative to the observer and their relative motion. This means that two observers moving at different speeds will measure time passing at different rates. Imagine two synchronized clocks, one remaining on Earth and the other traveling at a significant fraction of the speed of light. According to special relativity, the clock in motion will tick slower than the stationary clock on Earth. This difference in timekeeping, though seemingly bizarre, has been experimentally verified countless times. This phenomenon is not merely a theoretical curiosity, it has real-world implications. For instance, the Global Positioning System, or GPS, relies on highly precise atomic clocks aboard satellites orbiting Earth. These clocks experience time dilation due to their motion relative to clocks on the ground. To ensure accurate positioning, GPS systems must account for these relativistic effects. Section 5. Gravity's pull on time. General relativity adds another layer of complexity to time dilation by introducing the concept of gravitational time dilation. This phenomenon predicts that time slows down in stronger gravitational fields. In essence, clocks tick slower closer to massive objects compared to clocks farther away. Imagine two identical clocks, one placed at sea level and the other on top of a mountain. The clock at sea level, experiencing a slightly stronger gravitational pull, will tick slower than the clock on the mountain. This difference in timekeeping, though minuscule, is measurable with highly precise atomic clocks. This effect has profound implications for our understanding of the universe, particularly in extreme environments like black holes. Black holes, regions of spacetime where gravity is so strong that nothing, not even light, can escape, represent the ultimate manifestation of gravitational time dilation. Section 6. Real-world evidence of time dilation. The concept of time dilation, though mind-boggling, is not merely a theoretical construct. It's supported by a wealth of experimental evidence. One compelling example comes from the study of muons, subatomic particles created in the upper atmosphere by cosmic rays. Muons are highly unstable and decay rapidly. However, muons created in the upper atmosphere are observed to reach the Earth's surface in much greater numbers than predicted by classical physics. This discrepancy can be explained by time dilation. Due to their high speeds, muons experience time dilation, causing their internal clocks to slow down from our perspective on Earth. This allows them to survive long enough to reach the surface, even though their lifespans would normally dictate otherwise. Section 7. Can time stop at the speed of light? Einstein's equations suggest that as an object approaches the speed of light, time slows down significantly. At the speed of light, time dilation would become infinite, implying that time would essentially stop for the moving object relative to a stationary observer. However, reaching the speed of light is an insurmountable barrier for objects with mass. As an object accelerates, its mass increases, requiring more and more energy to continue accelerating. To reach the speed of light, an object would require an infinite amount of energy, which is physically impossible. Therefore, while the mathematics of special relativity suggests that time stops at the speed of light, this is a theoretical limit that cannot be achieved by any object with mass. Section 8. The enduring mystery of time. Time, once considered a simple, unwavering metronome, has revealed itself to be a far more complex and elusive entity than we ever imagined. Einstein's theories of relativity have fundamentally altered our understanding of time, demonstrating its intricate connection to space and its dependence on the observer's relative motion and gravitational field. While the concept of time stopping completely remains a theoretical curiosity, the phenomenon of time dilation is a well-established reality, supported by a wealth of experimental evidence. This mind-bending concept continues to intrigue and challenge physicists and philosophers alike, pushing the boundaries of our understanding of the universe and our place within it. The exploration of time is far from over. As we delve deeper into the quantum realm and the mysteries of black holes, we can expect even more surprising revelations about the nature of time and its role in the grand symphony of the cosmos.